So we've gone through electric force, electric field, and electric potential. Now it's time to take a look at different materials. And the first discussion we're going to have is about insulators and conductors. And then afterwards, take a look at dielectrics, which will become very handy in future discussions related to biological materials and applications to medicine. So this chapter is pretty short. We're first going to go through a quick recap of all the important equations and how to solve for electric potential. Afterwards, we're just going to hop into the main lectures and problems. There actually won't be too many problems here, mainly concepts. We're going to talk about insulators versus conductors, conductors in electric fields and their properties. Take a look at dielectrics, and then for both of them, we're going to discuss boundary conditions. At the very end, I'm just going to go through very briefly how we can apply our knowledge of dielectrics to biological materials, and then, of course, where dielectrics can be used in diagnostics. So let's start off with a review of electric potential. I'm going to go through a few important equations and basically a very brief overview of trends to know about from electric potential, as well as how to calculate potential. So some equations that we learned about, we already know the equation for work. I don't have to go through that again. Potential difference. We did derive another equation for potential difference using an integral form. But most importantly, we were able to define the electric potential difference as the change in potential energy divided by Q. So it's the change in potential energy per unit of charge. And that is equal to negative E dotted with a change in distance. So we can actually rewrite the equation for potential difference as the integral, or the negative integral from A to B of E dotted with dr. Now, if you're looking at a point charge, you have V equals to KQ over R, but sometimes you don't have a point charge. You have a large object that has a bunch of charge, and it's a continuous charge distribution. In those cases, either everything is uniform and you can sum it all up as discrete tiny charges, or if it's continuous, then you would want to use an integral just like we did before for continuous charge distributions and calculating electric fields. So in that case, you have V equals to the integral of K dq over R. The last thing we talked about was how to tie electric potential back to the electric field. There's actually another way of solving for the electric field, and that's through the potential gradient, where you have the partial derivative of the potential with respect to x, y, and z. And once you calculate that, you'll be able to get your electric field. Now, what are some trends that we learned about for electric potential? Now, this diagram is probably the most important one from the previous set of slides, or the previous chapter. If I have a point charge or a test charge that's positive, and I'm trying to move it towards another positive charge, we can see that it's going to have a lot more potential, because there's more potential for more energy to be released if we let go. Similarly, V is going to decrease as you move outwards. So that makes sense. If you have a positive test charge and you're moving it towards a negative charge, then the potential is going to decrease as you move inwards, because it's something that should happen. And then the potential will increase as you move outwards. Essentially, if you place a test charge within an electric field, it is going to move, it is going to want to move to an area of lower potential energy always. The last part to the chapter about potential was how to calculate potential. And one of the most important aspects is being able to navigate through the process of calculating the potential at a specific point within or outside a charge distribution. In those cases, such as this, where you have two shells, and in between there's some sort of, it's not super hollow. The inside is hollow, but not this. There is some sort of material within this. So there's going to be an electric field inside the core. There's going to be a second electric field in green. Let me just change this to laser pointer. So you have this point. We want to try and calculate the potential somewhere here, maybe even at the center. So in this case, I first have to figure out what the electric field is for each region. I know there's 1, 2, and 3 regions, so I'm going to call this electric field 1, 2, and 3 respectively. This radius is A and this radius is B. Now, if I were to calculate the potential from my reference point of infinity to any point along this line, then I have to do it step by step. So we first are going to start from infinity and then work our way in. So if I want to figure out the potential for this region over here, then V3 is going to be equal to the integral from, should be the negative integral from, let me just change that. I can put a negative there. Okay. So that should be the negative integral from infinity to any point r along this line in region 3 of E3 dr. So that gives you the potential for a point along this line in this region. Now, what happens if you want to figure out the potential at a point inside this blue region? So that's where electric field number 2 exists. So V2 is going to be, we're going to take V3 when r is equal to b to include all of this, and then we're going to subtract the integral from b to r, so any point in here, of E2 dr. So now you have this step-by-step process of going out to in, and if I want to figure out the electric potential at any point in region 1 inside here, it makes sense that I'm going to add this, and then a little piece of this to wherever my r is. So because V2 already includes V3, I don't want to add it again. All I'm going to do is say I'm going to take V2 at r equals a, and then add it to the potential from a to some point r over here. So V1 is going to be equal to V2 at r equals a minus the integral from a to r of E1 dr. And of course, if you want the potential at P, you would just go straight to 0. So hopefully that explains and gives you a good overview of how to approach calculating potential from infinity to a point, especially if you have different regions of different electric fields. So on to the fun stuff. This chapter is really visual, and I find it very fun. So conductors, the first thing we want to talk about is defining a conductor versus an insulator. You've probably heard of this before. Then we want to take a look at the properties of conductors, as well as how they behave in an electric field. Once we know how they behave in an electric field, we're going to be able to take a look at the boundary conditions to see what happens when an electric field hits a conductor. So insulators versus conductors. What are conductors? We've heard of this term quite a bit already. You've probably learned it in previous classes. Conductors are materials that have a large number of electrons that are free to move when they're influenced by an electric field. So normally they're just going to stay as they are because they're stable. But if you introduce an electric field, then there will be electrons that want to move along or against the electric field. So an ideal or perfect conductor usually has an unlimited supply of free charge. This is really not possible in real life, but when we consider a metal, it comes close to being perfect. So that is almost like one exception to the rule when we're taking a look at ideal conductors. So when we talk about a metal conductor, just assume that it's a perfect conductor, especially when we're dealing with problems. Now, we've talked about conductors being those materials that have a lot of electrons that can move around freely. The opposite of that would be an insulator, where the materials that are categorized as insulators have electrons that are not free to move around, and we call those bound electrons. So a dielectric material is what we're going to focus on in the next section. But a dielectric material is a type of insulator where some of the electrons are free to move around when an electric field is present. And that kind of movement comes in a very localized manner. It's not like the electrons are going to move from one side of the material to another. It's going to be slight movements to create dipoles and ultimately a polarization vector. So this is what we're going to focus on in the next section. So back to conductors. In the presence of an electric field, conductors are going to exhibit a very unique set of properties, and it's very important that you understand why these properties are the way they are. So there are some key electrostatic properties of ideal conductors when they are in the presence of an electric field. There are actually 5 main characteristics of conductors in electric fields, and these are really good to understand in detail. So first, I'm going to explain this diagram. This black rectangle is a conductor, and there's a green external electric field pointing towards the right. So inside this conductor, which is naturally neutral, the positive charges, just assume a positive test charge. If it's in the presence of an electric field, it's going to move along the electric field line. So in this case, the electric field is pointing towards the right, which means the positive charges are most likely going to be on the right. But why on the right? It's because the electrons are free to move, and they're going to move against the electric field lines, which makes sense. So with the electrons going towards the left side, you now have a negative charge over here, and you have essentially induced a positive charge on the right side. So we call this an induced charge. So over here, we have the electric field is 0 inside a conductor. That's the first property. And we want to understand why. So this induced charge that we have, that's negative over here and positive over here, even though I have an external electric field, if I have a separation of charge on either side of the conductor, I'm going to also create another electric field. Now it's going to go from positive to negative. So I'm just going to have this here. I'm going to have electric field lines going this way. So this is, we can label this as the induced electric field pointing towards the left. And this induced electric field is just as strong as the external electric field, but in the opposite direction. So inside the conductor itself, the electric field is going to cancel out and become 0. So that is why the electric field is 0 inside a conductor. Now, number 2, it says the charge density is 0 inside a conductor. And think of how this is due to Gauss' law. So since we've proven that E is equal to 0 inside the conductor, we can take a look at charge density. So we know that the charge can be related to electric fields through Gauss's law, where you have the flux being equal to Q enclosed over epsilon naught. So if E is equal to 0, then that means you have E times A is equal to Q enclosed over epsilon naught, and that means that E equal to 0 means Q is going to be equal to 0 based on algebra from Gauss' law. So try rearranging that to see why your charge density would be 0 inside a conductor, because Q enclosed is equal to 0. So the third one, it says a conductor is an equipotential. So how do we relate E equals to 0 to potential? So thinking back to the previous section, we had gone through all of the equations that are related to potential, and in particular, there was one equation that related electric field to potential, and the electric field can be calculated from the gradient of potential, which is just a bunch of partial derivatives. So if E is equal to 0, then what kind of value of potential gives you 0 after you derive it? If you think about it, a constant, when you derive a constant, it's always going to be 0. And a constant means that your potential is always going to be the same. So if the electric field is 0 inside the conductor, so 0 inside the conductor, it means that at any point inside the conductor, it's also got a potential, it got a constant potential, and therefore the whole conductor is considered an equipotential. So those three make sense so far. We can now move on to the next property of conductors and electric fields, where the fourth one says any net charge is going to reside on the surface. So just based on the diagram here, we already know that if we apply an external electric field to a conductor, the electrons are going to move against the electric field lines and therefore create an induced negative charge on the surface and then an induced positive charge on the other surface. And because of that, you end up having all of the charge being pushed out to the surface. Okay, so the last one says that the electric field is perpendicular to the surface just outside a conductor. Now, does this make sense? We kind of have to walk through the process. We know that all the charges are going to reside on the surface. So based on this diagram, we know it's always on the surface. And we also know that at any point on the conductor, it's an equipotential. So between these two, we know that for all the charges on the surface, they should also produce an equipotential. And therefore, the entire surface of the conductor is called an equipotential as well. So usually if you have a continuous shape, not a rectangle, if you have a continuous shape, all the net charge will reside on the outskirts or the very edge of your conductor. And at any point along that conductor's surface, you have an equipotential or the same potential. And because of this, the electric field coming from any conductor's surface must be perpendicular to the surface because of the same surface charge. So all in all, there are 5 different characteristics for conductors in electric fields, and it would be good to be able to explain each of these and why they are that way. Okay, so now we're just going to go through a few practice problems. They're not really practice problems, they're just examples that I want to walk through with everybody. We're just going to take a look at what happens to the charge distribution within a conductor after we apply an external electric field. So the first thing we're going to look at is a hollow conductor. So what happens if we have a hollow heart-shaped conductor like the one we have here? The electric field inside the cavity is going to be 0 since the charge is going to redistribute on the outer surface of the conductor. So we want to be able to show this. So we know that inside a hollow object, if we use Gauss' law and we enclose this area with a Gaussian sphere, we know that there's no enclosed charge. So simply put, we have E equals to 0 over here. Okay, so we now have E equals to 0, and next we want to take a look at the charge distribution within this blue area. So if we consider it to be neutral and we have the external electric field pointing towards the right, it means that your negative charges are going to move towards the left. And so you have something like this. And that means if I have a bunch of negative charges on the left, all of the positive charges will be pushed to the right, or essentially there will be a positive charge distribution on this side. So all in all, the electric field inside the cavity is 0. And the charge is going to redistribute onto the outer surface of the conductor. The object itself was neutral to begin with, so even if I have a Gaussian sphere around the entire heart-shaped conductor, the total charge is still going to be 0. But the surface charge might be different on each side. Okay, so the next example we have is what happens if we place a charge outside a conductor. So we have a positive charge plus Q on the left, and then we have a conductor in blue on the right. So if this is positive and this is neutral, what happens if we place it in the presence of an electric field going this way? So in the conductor itself, which was originally neutral, you have your negative charges going to this side. They're very big negative charges. Now you have positive charges on this side. So that part makes sense. But now we have this additional test charge plus Q on the left side. So what is going to happen here? We know that it's a positive charge. Originally, the object was neutral, but we introduced an electric field to it, and therefore the left side, which now has an induced negative charge, is going to attract the positive test charge on the left. So that makes sense. So we're going to go with something a little bit more difficult now. What happens if you place a charge inside a hollow conductor? And now I've kind of drawn this wacky shape because it doesn't matter. We just have a conductor with a hole in it. And inside that hole, we've placed a positive Q charge. So what will happen here is, first of all, remember that the conductor itself is neutral, but there are electrons inside it that can freely move around. So if I have a plus Q over here, then it makes sense that the negative charges would kind of group around onto the inner surface, like this. And once it groups around into the inner surface, it makes sense that it's left the remaining part of the conductor with a positive charge. And with conductors, any net charge only resides on the surface. So that means you have a bunch of positive charges all over the surface. Probably just very hard drawing with the mouse. Okay, those are my positive charges on the surface. So we know that the electric field is going to be 0 inside the conductor. So always remember that inside a conductor, E is always equal to 0. Okay, so if we also apply a Gaussian surface, we know that the flux over the closed surface is going to be 0. So let me just change to a different color. If I create a Gaussian surface in green over here, I'll be able to enclose this charge and this plus Q charge, as well as the inner surface of the conductor. Now, from this, I also know that the enclosed charge is going to be 0 because plus Q attracted a total negative surface charge of minus Q onto the inner surface. And therefore it pushed, it pushed positive Q onto the outer surface. So you will have to be able to label diagrams properly to show what kind of charge is on the surface based off of the placement of a test charge, for example. So if the conductor is electrically neutral, the charge will become plus Q. So that's just important to remember. Sometimes there will be questions where maybe the surface already started with a plus Q, and then this may become plus 2Q instead. So let's take a look at another example. What happens when we ground the conductor? So we already have an overview of what happened before. The minus Q is going to attract minus Q onto the inner surface and therefore push a charge of plus Q onto the outer surface. What happens when we ground a conductor is that we're going to connect it to the earth as well as its unlimited supply of positive and negative charges. Now, if I have plus Q on the surface, then the ground is going to provide me with enough electrons to balance out the charge on that surface, and therefore you are going to end up with an external surface charge of 0. So that is something that's very important to understand when we ground conductors. Another thing to note is sometimes there may be various surfaces within a conductor. It could be many concentric shells. some examples may choose to ground specific surfaces within that shell. So just be careful how you do the calculations, or not calculations, how you draw the diagrams to make sure the proper surface is being grounded based off of the diagram. There's something else I want to mention about this, and it's also because it's because we want to find differences between grounding and not grounding a conductor. So in the previous example, we know we end up with a plus Q charge over here. And then on the example to the right, or the next example, when we ground it, you don't end up with a plus Q charge on the surface, but rather 0. And when you take a look at the overall net charge of the entire object, if I create a Gaussian sphere over the whole thing, so I can't really draw it here, but imagine creating a Gaussian sphere that envelops the entire conductor, then that means you have 0 plus Q minus Q, and therefore you have an enclosed charge of 0. So that is different than the previous example where the enclosed charge was plus Q minus Q plus Q, so therefore it was plus Q. Okay, so next we want to figure out what happens when we release a charge onto a conductor. So what would happen if we touch a conductor with a charged rod, and where would the charge go? Essentially, the simplest answer to this question is if you touch a conductor with a charged rod, any of the charge is going to go on the surface of the conductor, or it might take away some charge from the surface of the conductor based on what the charged rod is like. So the extra charge has to go to the surface, as it cannot be distributed into the volume of the conductor, because all net charge must reside on the surface. So I have two examples to go through with this. In example number 1, I want to ask what happens if we put a charge on Q1, or conductor 1. We put charge Q1 on conductor 1. And then also a charge Q2 on conductor 2. So that would be me bringing a rod over here with a charge of Q1 and touching it, and then it transferred Q1 onto this conductor. Same thing over here. I have another rod, and I've transferred a total charge of Q2 onto this conductor. So now both of these have different amounts of charge, and these two conductors are completely separate with, and they're not close to each other at all. Now, what happens in example number 2, what happens if we connected the two of these together through a massless conducting string? That would be between these two over here. So if that happens, then what happens to the charge distribution? We know that there's Q1 and there's Q2, so the total charge is Q, where Q is equal to Q1 plus Q2. So since these two conductors are now connected through another negligible conducting string, we can consider it as one system. And so the charges are going to redistribute until they act as one conductor. And the requirement for a conductor is that its surface must be an equipotential. So the guarantee for us is that any point on the surface of conductor 1 or conductor 2, whether it's here or here, it must be at the same potential. So if you want to figure out the charge distribution on conductor 1 and conductor 2, all you have to do is set V1 is equal to V2, where each V is equal to KQ over R, and then just rearrange to solve for Q for each conductor. So the last section I want to talk about is the boundary conditions that we have to consider when we take a look at conductors and electric fields. So if I have a conductor surface over here, this means that when an electric field penetrates the surface or hits that surface, there's going to be a normal component and then there's going to be a tangential component. And the angle from the normal is theta. So boundary conditions, to simply define them, they help us define how electric fields and induced charges relate to each other at the boundary or at the interface of two media. So at the interface of two media, that's a discussion we'll have later on about dielectrics. But for conductors, what we can do is have a very simple overview of tangential and normal boundary conditions. So think of an incident electric field vector that has a tangential and normal component. We're going to have to analyze and find the best way to analyze each of these components. So there are two things that we can take advantage of. We know Gauss law and we know about potential. So let's go to the next slide, and we're going to first target tangential boundary conditions. So at the boundary over here, in blue, we know that the conductor's surface is an equipotential. So at any point along this line, it's an equipotential. So we're going to start by analyzing the potential at the boundary. One thing we note is that we can take advantage of line integrals on a closed path. So over here, if we have a closed path, we do know that it's an equipotential, so the change in potential should be 0. We know the equation for change in potential. We know it has to be equal to 0, and therefore we have ET, and this is a closed path integral because we're just going to close the whole thing as a loop. So we know that there's some sort of ET, or tangential component to the electric field, and it travels from A to B over a length of delta W. So we have ET delta W. But this whole thing, because if I start from A, go to B, then C, then D, then A, there's no change in potential whatsoever, and therefore it's going to be equal to 0, and therefore ET is going to be 0 at the boundary of a conductor. So that actually proves to us that there is no tangential component at the boundary of a conductor, and all the electric field lines are going to be perpendicular to the surface. Now we take a look at the boundary conditions. For the normal component, we're going to use a pillbox and take a look at the surface that way and see how much charge is enclosed through Gauss law. So over here, we have our pillbox in green, and we're going to be as close to the surface as possible, where we have a change in thickness called delta. We know Gauss law says that the integral of E dotted with ds is q enclosed over epsilon naught. Well, we know that the electric field is the normal component, and we know that the change in, we know that the integral of ds is simply the change in s. This is then, or not change in s, this is the surface area. Then we know that we have the enclosed charge being the surface charge density multiplied by the surface area, and then divided by epsilon naught. But these two areas cancel each other out, and you get En equals to negative rho s over epsilon naught. So rho s is essentially the surface charge induced on the surface of the conductor, and note that it is a constant. So if there are two things we note from this. If the electric field, or the normal, is going into the conductor, that means that your surface charge density is going to be less than 0. That makes sense because negative charges will have electric field lines coming towards it. Now, if your if the normal component of your electric field is coming out of the conductor, then that means you're going to have a charge density that's greater than 0, and that makes sense because positive charges will have electric field lines radiating out of it. So all in all, these two types of boundary conditions actually help prove the different characteristics of conductors. Being able to explain those 5 different characteristics, like I said, would be very, very important. So in this section, we're going to start our discussion about dielectrics. I consider this to be the main section of this chapter. Even though conductors are very important and it's good to be able to visualize them and draw diagrams related to conductors, it's also very important to understand what dielectrics are. So I will go through a little bit of the derivation of some of the equations, but you will not be expected to be able to replicate that, of course. The most important thing is to understand the concepts behind dielectrics. So let's first start off. What is a dielectric? We're going to redefine an insulator as a material where the electrons are tightly bound to the atom with negligible macroscopic movements. No material is a perfect insulator. So if you have an applied electric field, sometimes there will be localized changes within the charge distribution. So in that case, we look at dielectrics, and a dielectric is an insulating material that can be polarized when an electric field is applied. So if I have, let's say, this object over here in its neutral state, it's got a positive charge and a negative charge. Upon the application of an electric field, if we zoom in really, really close to this object, then there's going to be a slight charge separation where one end is negatively charged and the other end is positively charged. So think of this as, for example, the water molecule where one end is positively charged and the other end is negatively charged. So this creates a dipole. And if you have a dipole, it means that there's going to be a direction of polarization. So essentially, where or what direction are these molecules having this charge separation? So a polarized dielectric is quite different than a conductor because instead of having all the negative charges on the surface of on one side and all the positive charges on the surface of another side, you have to think of the entire material broken up into tiny little pieces. And each of those tiny little pieces has a dipole with a charge separation. So if I have an electric field that's applied over here towards the right, so I'm just going to write this down. Let's say we have an electric field going this way. So if I have an electric field going towards the right, it means that within each of these dipoles within this object, negatives are going to be on the left and positives are going to be on the right. Now, for all of the dipoles that are located on the left surface of this object, the negative side of the dipoles will be exposed, and on the right side of the object, the positive side of the dipoles will be exposed. So one thing for sure, we know that we do have some sort of induced surface charge on each end. But what's also important is there will be a charge inside the volume itself, unlike a conductor. So we have these induced surface charges, but we also have an induced volume charge in here. And so sometimes it may not be zero, but in here we have what we call rho V for your induced volume charge. So overall, how can we define all of this, or how can we characterize what happens when an electric field is applied to a dielectric? We have a term called the polarization vector, P. So it can be determined by constructing a small volume, delta V, so maybe we take this one little dipole, around a point, and then we add all the dipole moments vectorially within delta V. So essentially it's a summation. You're trying to figure out the polarization vector by summing up all of the different directions of all the dipoles within a certain volume, where each individual dipole is equal to Q times D. Now, when you're calculating the induced charge, are there any equations to help us do this? Yes, there are. I'm not going to go and derive it, but in polarized dielectrics, it is useful to be able to calculate the induced charge. There's the surface charge, which I talked about, represented by rho S, the strength of the polarization vector, dotted with the surface normal vector, is going to allow us to figure out the induced charge density on the surface. So that makes sense because the strength of the electric field and the direction of penetration of the electric field into the material will directly affect the surface charge density. Now, taking a look inside the volume, it's a little bit different. Instead of taking a look at the direction that the electric field penetrates the surface, we're going to take a look at the different rate of change of the polarization vector within the volume itself. And so we have another equation for rho v that involves the gradient dotted with the polarization vector. So these equations are useful to have. They are things that you will not be expected to solve problems with. So next, I do want to go back a little bit and talk about Gauss' law. Gauss' law was good for conductors. It was good for objects with some sort of net charge or Q enclosed. But if you have a dielectric, things do change a bit when it comes to Gauss' law. There is a reason for this. So Gauss' law for electric fields will be affected by dielectrics. The local electric dipole moment, or the polarization event that takes place, is going to displace the electric field slightly. So that has to be taken into account when we're looking at these materials. So we're going to define a new type of electric field that helps cover this. So we call this the electric displacement field. It simply is called that because it's how much the polarization has displaced the electric field. And it's pretty much defined as that. The displacement field is equal to epsilon naught E plus the polarization vector. So that will give us an overall displaced electric field within a dielectric. So now that we have this displaced electric field, it means that we can't really use our regular definition for Gauss' law. We have to update it for dielectrics. So we have to redefine Gauss' law for the displacement field. We know that the charge density is no longer just the free charge that you have on the object. You also have the induced volume charge from the dielectric. So we add those two up and you end up getting the integral of d dotted with ds is equal to q enclosed free. So that free just means how much free charge is on the surface of the object. So this is Gauss' law for dielectrics. So this is the free charge enclosed within a specific amount of surface. So we now move on to the dielectric constant. It is important to know that about the dielectric constant. I will slightly derive it for everybody. First, we have to define what it is. Because different materials will be affected and have different resistance to electric field displacement, that means that having a dielectric constant or some sort of parameter will allow us to either recognize the material or see how it affects the electric field. So a dielectric constant, simply put, is something that measures how strongly a material can polarize with respect to free space. And why would you think this is helpful? It's because based on the material you have and the electric field that's applied, you can determine the displacement vector. You can determine the displacement vector as well as the polarization. And from the polarization, you will then be able to determine the induced charge densities within the material. So kind of have to work backwards. So a lot of dielectrics are highly linear. So we can assume that the polarization vector is usually proportional to E. And so we're going to define chi E as the electric susceptibility factor. So we have this equation over here to use. And we're going to use the previous equation for the displacement vector by replacing P with this term. So once we have this replaced, we have epsilon naught times 1 plus chi E times the electric field. We call this 1 plus susceptibility factor. We call this the dielectric constant because that's how much the material is susceptible to change from the electric field. And so this can be simply replaced by epsilon r, which you should be fairly familiar with and have seen in numerous different equations, especially when it comes to capacitance, for example. So now that we have d, the displacement vector, being equal to epsilon naught, epsilon r, and then e, we can combine these two to just epsilon. and this means absolute permittivity. So it is important to know where this dielectric constant comes from and why it's useful. Now the last part, boundary conditions. Boundary conditions for dielectrics, we can go through a bunch of different practice problems for this, but the main goal is to get you to understand where it comes from. So for dielectrics, it's a little bit different than conductors. With conductors, we were able to apply the potential difference as well as a loop to try and figure out an expression for the tangential component of the electric field. But in this case, for the tangential boundary condition, we now have this expression. It's no longer ET is equal to 0. There is a dielectric and it's not a conductor. So we know that the tangential component of the electric field really should be continuous at the boundary. So I'm not going to derive this, but it comes once again from the line integral. For the normal boundary condition, we're going to use Gauss' law again and try and create that pillbox through the surface of the dielectric. What we'll find is that the normal of the displacement vector is going to be continuous at the dielectric-dielectric interface, because at this interface, there is no free charge. So this is important to know, and this leads to the fact that the normal component on one side of the dielectric will be equal to the normal component on the other side of the dielectric. And that is about it for dielectrics. We can then move on to why they are useful in biology and medicine. So let's take a look at applications to life and medical physics of dielectrics. There wasn't a lot to look at over here because it's really straightforward in terms of just figuring out what the dielectric constant is for different biological tissues and cellular structures. What I really want to go through is the kind of research that's being done now, as well as how one can actually figure out dielectrics in biological tissues. So let's first start off with a brief history of when we even started thinking this could happen. So there's a long history of studying dielectrics in biological tissues. The main thing that was tested was current on different biological samples. So as electricity and magnetism were being fleshed out, people would start to test the effects of currents on biological samples like skin, blood, things like that, and to see how much polarization there would be once the samples were affected by applying voltage or some sort of current. Now we know that that does happen to different degrees and different types of materials. So the focus now is on how the electric fields can affect the dielectric properties of biological systems. So if we apply an electric field, how will one particular type of tissue respond? For example, a healthy tissue, and how will a cancer tissue respond? So these are things that if we are able to find a way to differentiate between the effect of an electric field on the dielectric properties of two types of tissue samples, we'd be able to help in diagnostics. So this type of analysis is primarily used in biomedical engineering, where new insights can be found on how electric fields act on cells and tissues. So like I said, it can be really beneficial to applications of electric fields and currents. So as you can see in the bottom over here, I got this article and all this information from one article from 1989 that did a review of all the dielectric properties of tissues and biological materials. It's the only one that I've been able to find that has a full text, but I would encourage you to take a look at the different types of dielectric properties and also the different reviews that are available, just so that you can learn more about it for interest's sake. We won't be tested on it, but just if you are interested in dielectric properties in biological tissues, you will be able to find a lot of that information in biomedical engineering journals. So next, I want to discuss what happens once you do apply an electric field to biological samples. If you apply an electric field, it's going to cause several different relaxation events within that sample. And depending on whether your sample is healthy versus unhealthy or diseased, the relaxation event will be changed, and therefore you'll be able to calculate the differences in dielectrics. Now, if you want to know all the details, this review is very, very long. It's like 80 pages, but it goes through all of this in detail, as well as the derivation of all the equations and simulations used to help determine and interpret the dielectrics in biological tissues, things that I won't be going through in the lecture itself. So from this, when we're talking about dielectrics in biological tissues and relaxation events, there are three different processes that are responsible for dielectrics in tissues. So these are the three main factors that affect dielectrics. There's something called interfacial polarization. So basically, this is a result of the boundary conditions that we talked about before. At the interface between two phases, there's going to be dispersion that occurs in bulk properties when the material interfaces are charged. So once you charge an interface, there will be a distribution or dispersion of charge that can be associated with some sort of polarization along the surface. So this is what that refers to. You then have dipolar orientation. So that would be a partial orientation of permanent dipoles. The best explanation for this is, or the simplest one, is when you apply an electric field, all of these dipoles are going to approach thermal equilibrium with first order kinetics. And the type of relaxation involved is called Debye type, which I won't explain. It is explained in about 20 pages within the review. But dipolar orientation, the main thing is you now have a reorientation of all these permanent dipoles. Last one is ionic diffusion. If you have an electric field that's applied and you have a redistribution of charge, also dipoles being oriented in a different way, that means that you also may have diffusion of ions across or onto the surface. And it's because of these two that causes ionic diffusion, and these are effects that are due to the polarization of counter ions because of the effect that the electric field had on the interface and the dipoles. So these are three main relaxation processes that are commonly used to determine dielectrics in biological tissues. The other thing this article goes through is what happens when you apply electric fields or you try and determine dielectrics at different frequencies. So one thing that they found out is that as you increase the frequency, there's going to be an increase in conductivity. And that is attributed to an increase in the volume fraction of the suspension of the sample that you're looking at. That's accessible to the applied current. So more of it becomes available to become polarized, for example. So what can be affected at low, medium, and high frequencies? At low frequencies, only extracellular fluid is available to current flow. So that's useful in explaining conductivity in blood, but not so much for complex membranes. Once you up that to 1 to 100 megahertz, tissues are then equivalently or equally electric in property to different suspensions of proteins that are non-conducting, like an electrolyte. When you go to microwave frequencies, you end up over 100 megahertz. Usually the dielectric and the relaxation events plateau around 10 to 100, so anything past this is just too much. But at that point, everything is governed by the dielectric relaxation of water and the loss of small side chains and small polar molecules attached to those proteins, for example. So all in all, what's happening here is just an overview of how different frequencies will allow us to detect different changes in dielectrics for different types of samples. Last, there have been quite a few studies in the past 10 years about how microwaves can be used in diagnosis and treatment of different diseases. So in the medical field, microwaves aren't just useful for diagnosing, they could also be helpful for treatment if we can understand how they affect our cells and tissues. So detecting disease is a huge thing nowadays, and through microwave methods, there's something that's called cavity perturbation. So in order to use this method, you actually have to know the dielectric properties of the biological material you're sampling. So cavity perturbation is when you determine the dielectric properties of human bile, bile stones, gastric juice, saliva, etc. by measuring a change in permittivity within a cavity. So let's say you're looking at your gallbladder, or you're looking at your kidney, one of the organs inside your body, whichever one you choose. Within that cavity, you're going to hone in to a specific area, and you're going to change the field very slightly in that cavity and see if there are any changes within the dielectrics. And then you're going to go around the entire organ or the entire sample or entire region, and you're going to see if there are any areas that react differently, and that may be an area that's associated with disease. So, as I said here, normal versus infected samples, like bile, will have different dielectric constants and loss tangents, and the constant itself is going to vary from patient to patient, but there is a consistent increase or decrease in signal based on what kind of infection you have. So this paper, if you want to learn more about it, it goes through a review of how they were able to detect normal versus infected samples of bile between different patients. So that's pretty much it for the applications of dielectrics. There's still a lot of studies being done on how to measure and accurately interpret changes in dielectrics, but they are commonly used in medicine, specifically diagnosis and treatments. Okay, so for a summary, I just want to go through some key concepts and important equations. Like I said, there weren't too many problems here except visual ones. So my focus is on you being able to understand the properties of conductors in electric fields, know why these 5 properties exist based off of a simple diagram. Afterwards, know how we can apply Gauss' law in dielectrics. So we already know how to use Gauss' law. The only thing that's different now is we have a displacement vector due to a polarization vector, and we have updated Gauss' law for dielectrics by saying it's the integral of d dotted with ds is equal to q enclosed of the free charge. And just keep in mind, there is no epsilon naught because the epsilon naught is already in the equation for the displacement vector. So all in all, that's it. Definitely also be able to draw and label diagrams for conductors and dielectrics so that you can show different charge distributions after an electric field is applied.